All right. Hello, hello, hello. Okay, so in the last video, we talked about the two classifications of forces, field forces and contact forces. We talked about our four fundamental forces, which are basically just the four field forces. And then we talked about our three flight forces, which don't necessarily actually have anything to do with flight. Two of them have to do with flight. Drag is something that everything has to deal with. Really anything moving through any fluid. And bear in mind that air is a fluid. So that's why the atmosphere exerts drag force on your car when it's driving. Water also exerts a drag force. It's what causes erosion, is that force kind of brushing things past. Today, though, that's not the main point of our video. Today, we're going to talk about the other five forces. These five are all contact forces. Okay, so we're going to work our way through these. You've probably heard of a couple of these. Some of them are more complicated than others. Some of them I'm going to spend a fair bit of time on. Some I'm going to say, hey, this exists, and then I'm going to move on. Because until we start doing free body diagrams, these just really aren't going to make too much sense. So let's just go. So there's five of them we're going to be going through. First one is the normal force. Second one is friction. Then we have buoyancy, or the buoyancy force, tension, and applied forces. Okay, now each one of these has a variable that we use to represent it. As a general rule, we always use a capital F to mean force, and then we put a subscript on that capital F to identify which kind of force we're talking about. So that's kind of how we tell the difference between those forces. I just realized whiteboard wasn't up, so I'm going to fix that, and I'll be right back. Okay, now, no. These aren't too terribly complicated. They should make sense to you once you start seeing them. So, normal force, it's a force, so we're going to use... Oh, I need to fix my pen, too. One second. All right, take three. So, normal force is a force, so we start with an F, and then we put a subscript of the first letter of the name of the kind of force. So, for us, it's going to be an N. Okay? Now, generally, we use capital letters for all of these, with the exception being applied force and friction. So the frictional force is F sub F. Buoyancy force is F sub B. Tension force is F sub T. And applied force is F sub A. As a quick little side note, for our fundamental forces that we talked about in the last video, we use F sub G or F sub G to represent the gravitational force. Generally, we're going to be using this one because we're going to be talking about stuff near the surface of the Earth. Then we have F sub EM for electromagnetic. And then, of course, there's electric force and magnetic force, but we're not going to be messing with those. And strong force and weak force, we're not going to be doing anything with, but they're Fs and Fw. Okay, then we have drag, thrust, and lift, and we use lowercase letters for those three. So Fd for drag, Ft for thrust, and Fl. I use a cursive L when I'm doing this, but because I don't want it to look like a 1, if you want to use a capital L, that's going to be fine. But you're going to need these abbreviations. So if you didn't write them down while I was putting them up, pause this, go back, and write them down, because you are going to need them when we start doing free body diagrams. All right, cool. I'm going to erase all this. Now, we are going to start off with the normal force. Now, the normal force is the force of support. Okay? Now, normal, you need to understand what normal actually means, and I think that's going to help some. So if you have a surface, hey, the pen's not on. If you have a surface, okay, it could be a tabletop, could be the floor, could be a chair, could be the roof of your car, wherever. Okay, normal is defined as perpendicular to. Okay, specifically away and perpendicular to. Okay, so if you're on a slide, okay, then normal to the slide is perpendicular to that slide. Okay, so we call this the normal force because it is the perpendicular force. Okay, it's the support force, the force of support, so it's always perpendicular to your surface of contact. I currently am standing on the floor. Okay, so gravity is pulling me down. Well, why am I not falling? Gravity is trying to make me go that way, but I'm not going that way. Well, because I'm standing on the floor. The floor is supporting me, exerting a counter force to gravity. So the normal force in this case is up. When you're going down a slide, in the example I was using earlier, that's not a very good slide. Let's do it with that. Okay, when you are going down a slide, gravity is still pulling you down, but there is a normal force. I'm going to erase this. There is a normal force that is perpendicular to the surface of the slide. Okay, so we have gravity pulling down, normal force perpendicular. And this is a really good spot for me to point out. There's also friction in this. So I'm going to leave this up, and we're going to come back to this in a second. Hopefully you all know where the friction is, but we're going to make sure. Okay, got it. Okay, now, what about on a roller coaster when you're up at the top of it? Okay, so we're on a roller coaster. We go through a loop and then continue on our way. When you are here, what direction is the normal force? Well, it's perpendicular to your surface of contact, specifically towards you from the surface of contact. So the surface of contact, we zoom in on this. This is your little cart. Surface of contact is this right here. So perpendicular means it has to be this way. Okay, it's counteracting that force. It's exerted anytime two objects are physically in contact. There is a normal force. There's not always friction. There's not always tension. There's not always there's not always buoyancy. There's not even always an applied force or tension force. But there is always a normal force when two objects are contacting each other. One of the common points of confusion we see in physics is people mistake the normal force and gravity for a third law pair. They are not. They do cancel, but they're not a third law pair. We're not going to spend too much time on that right now, but they're not a third law pair. So that's our roller coaster. Normal force, force of support, it's always going to be perpendicular to the surface of contact, but it doesn't have to be up. It can be down in certain circumstances, like a roller coaster. All right, now let's talk about friction. Friction is probably the force you should know the second most about. Hopefully, gravity you're pretty familiar with too, which is always down. But for friction, friction is just the resistance force. Okay, it opposes motion. It does not oppose change in motion. Don't confuse friction with inertia. Inertia, something that is moving, will want to continue moving. Friction just wants everything to stop moving. Stand still, be there, that's friction. Okay? It opposes motion, or it opposes attempts to create motion. Okay? So this is, like I said, it's the resistance force. So if something's moving, it's really obvious which way the friction is, okay? If you are, let's go with baseball, softball. You're sliding into a base, okay? So you're on the ground. You're on the ground. There's the base. And you are sliding towards the base. Okay? Hopefully you don't hit it too hard because that base is going to break your ankles. But friction, if you are going this way, then friction is going to be the opposite direction. Friction is always going to oppose the motion. Now, what if you are standing still on a ramp? Okay, you're not moving on the ramp, you're just standing there. Well, while you are standing there, there are three forces that you're dealing with. Gravity, which is always present, is going to be down. The normal force, the one we just talked about, is perpendicular to the surface of contact. But there is another force, friction. There is friction when you're on this ramp. You're not moving, but there's still friction. Because if there wasn't friction, you would be sliding down the ramp. So if you are trying to move this way, that means friction has to be in the opposite direction, opposing that attempt to move. So friction is up the ramp in this case. Likewise, on the slide, if you are moving down the slide, obviously there is also a frictional force up the slide trying to slow you down. And if you're, like if it's summer and you're going down the slide, you may have really high friction and when you're sticking to the slide trying to go down. So friction is still going to be there. You need to know, this is probably a little bit of new material here, B. You need to know that friction is directly proportional to the normal force that is being experienced. Okay, the larger your normal force, the higher the frictional force that's going to be exerted on you. Okay, and we're not going to do any math with that. There is a math to calculate frictional force. We're not going to do that in this class. That's physics class. We'll save that for there. It is always opposite the direction of attempted motion. So for a book sliding across the table, let's do this. So here's our tabletop. Here's our book. Okay, if the book is going this way, then the frictional force has to be this way. And once again, we would also have Fg down and a normal force up. Standing on a ramp, I already talked about that. Walking. Okay, walking is weird. And I know that sounds stupid, but walking is weird. Okay, so I'm going to try my best to draw this. Okay, so let's say this is your shoe, and this is the floor. Okay, you are trying to walk. You want to go this way. Well, when you do, you are pushing yourself forward. Your foot is actually trying to go this way. Your foot is trying to slip backwards. Don't believe me? Try running on tile in socks. Okay? Your foot will just slide. Okay? That's what's trying to happen. When you don't have friction, your foot just goes backwards. That means the frictional force when you are walking, the frictional force that you are experiencing is actually forwards. Tires on cars are the same way. They're trying to spin, and because they're trying to, the bottom of the tire is trying to go this way, the friction between the tire and the road makes the car go that way, because the friction is what's pushing the car forward. Airplane tires don't work this way because they're all free spinning. Okay? We'll do more with that later, but that's the example of friction sometimes causes things to move, like in our shoes and our tires on our cars. Okay? Friction actually pushes that object forward. All right, that brings us to buoyancy force. Buoyancy force has a lot of stuff here, but it basically sums up to buoyancy, buoy. When you see buoys on lakes or in rivers or ocean, wherever. Buoy literally means floating. Okay, this is the floating force. Okay, this force causes things to move up. Every object that is immersed in a fluid is experiencing a buoyancy force, including you right now. The atmosphere is a fluid. It is exerting a buoyancy force on you. However, the atmosphere is a very thin fluid. It's not a very dense. You can see this better with a fluid like water, which is a lot more dense than the air. When you are immersed in water, you can feel that buoyancy force. It pushes you up. The atmosphere is doing the same thing, but generally we ignore the buoyancy force of the air unless it matters. If we're talking about a balloon, then buoyancy force on the air, really, really important. Okay? If we're talking about a car driving, buoyancy force of the air is negligible. It is so small as to be irrelevant. So the more dense the fluid is that the object, whatever, is immersed in, then the greater the buoyancy force it's going to experience. Okay? If I was immersed in mercury, I would experience a very, very great buoyancy force. In fact, you can almost lay down on top of mercury because the buoyancy force it exerts is so great, because it's so dense. Water you can float in, obviously. The atmosphere, it's trying to make you float, but it's not nearly strong enough. So, buoyancy force is the upward or buoying force that fluids exert on anything that is immersed. Immersed means surrounded by. So, like, if you have an ice cube and you push it down in the water, it's immersed in the water. Your finger is also immersed in the water if you put it in the water. Buoyancy force directly proportional to the density of the solution or fluid, which is what I was saying a second ago. Mercury is going to exert a greater buoyancy force than water. Water exerts a greater buoyancy force than air, but they all exert a buoyancy force. If it is a fluid, that means gases or liquids, then it's going to exert a buoyancy force. Okay, atmosphere is a mixture of fluids. We don't float away. Already talked about that. Less dense objects float on more dense solutions. So, I feel like that's pretty self-explanatory. Logs will float in the water because the wood is less dense than the water. Helium balloon will float away in the air because the buoyancy force of the air is very, very strong compared to the weight of the helium. And then a treasure chest on the bottom of the ocean. Well, it's so heavy that the water buoyancy force isn't enough to make it move. If you took that same treasure chest and immersed it in mercury, it probably wouldn't sink all the way. It would sink down part way and eventually find a point where it could partially float. In my day, we called that flinking, floating and sinking at the same time. Okay, that's pretty much it for buoyancy. I'm going to draw out a quick little diagram for these. So the log in the water. Okay, so what forces are on it? Well, we still have weight. We always have weight, Fg down. There is going to be no normal force this time. Okay, there's no normal force here because it's not two solid objects interacting. Okay, but there is this time a buoyancy force being exerted by the water. Now, if the water is moving, then there might be drag as well, but it just says floating in water, not floating down a stream. Then there's the helium balloon. So if we have our helium balloon, there's our string. There's going to be weight, again, always. Weight down, Fg. Pretend that's a G. And there's going to be a buoyancy force that is lifting it. The air is pushing that balloon up. In this case, very successfully. And then treasure chest sitting at the bottom of the ocean. Oh, by the way, again, there is no normal force here because there's not a solid object interacting. It's just one thing, the balloon. However, on our treasure chest, Okay, on our treasure chest sitting on the bottom of the ocean, it's underwater. So it's going to be experiencing a buoyancy force. It's also going to be experiencing gravity. And there has to be a normal force, which is also going to be up because it's in contact with the ground. That's another solid material. Okay, so there's going to be a normal force here. So we have two forces up, one force down, and this thing is still not moving because gravity is stronger than both of them. Okay, if this is in a river, well, we're not going to mess with that. All right, and that brings us to our last two, tension and applied. I'm not going to do too much with these. Tension is not a real force. Tension is more a force transmission. Okay, so let's go with the tug of war example from the worksheet that you guys worked on. If you have two folks playing tug of war, they are both experiencing a tension force. Okay, so this person, I'm going to make these guys two different colors. Pretend those are his arms. Okay, so this guy's tension is going to have a force because they're both on the ground, obviously. So there's going to be weight down, Fg, gravity, normal force up, and he's going to be experiencing a tension force pulling him this way because this guy is pulling on the rope. So his force that he's applying to the rope is being transmitted through the rope to the guy on the other side. Now, this guy is also being pulled. The rope is trying to make him slide. That means there's also a friction force pulling back the other way. So there's four forces for this guy, and there would be the same four forces for the one on the other side. We'd have an Fg. Hey, my alarm's going off. One sec. Okay, so there would also be the same four forces here. We'd have a gravity force down, a normal force up, friction this way because he's trying to move in the other direction, and a tension force going this way. So you can see how these forces can get pretty complicated. Now, again, tension is frequently just transmitting something else. If you think about a wrecking ball, okay? So we have wrecking ball hanging at the end of a long string, cable, whatever, that's attached to a crane doing whatever. If we're doing the forces on the wrecking ball, okay, then there is going to be a tension force up, okay, along with the weight down. Anytime you have a chain or a rope or a cable or a string of any kind, there's going to be tension in that string. Okay, we're going to call it line. Anytime there's any kind of line, there's going to be tension in that line. Okay, that's what dictates whether tension is present or not. Okay, that's pretty much it for tension. Applied is just our catch-all force. So we call any applied force is the push or pull that you've always heard about. So if I shove a table or shove a chair, so let's say, hey, turn the pen back on. So here is a chair, and I give it a push, and it is sliding, and I gave it a push, and it started sliding this way. Okay, while I was pushing on it, there was an applied force. I was applying a force to the chair. Okay, once I let go of it, that applied force goes away. Okay, so that applied force it's kind of the catch-all. If you're like, something is pushing here, but it doesn't fit into any of the other forces we've talked about, that's going to be an applied force. Okay, and that is pretty much it. Yeah, generally applied force is going to be coming from a person pushing on it, or like in the example of the tug of war, if you were doing it for the rope, then there would be two forces being applied, one from the person on this end pulling this way, another from the person on this end pulling this way. There's two applied forces. Those applied forces become tension forces while the rope is transmitting them to the other person. Okay, and again, right now, just focus on learning what's on here, and then we'll start doing free body diagrams where you start actually figuring out what these forces look like. We'll do that next, after you've had some time to digest all of this. So that is it for today. Have a wonderful day, and I will see y'all next time.